So welcome. We start this lecture with the important and interesting concept of one parameter subgroup. These are subgroups of G, if G is any Lie group. We can study subgroups with the following property. So this is the definition of the concept of one parameter subgroup. And first, an example that actually we have a well-known example. Imagine a rotation of vectors in plane xy. So here is some vector A, and we rotate it with this by angle alpha first, and then additionally with angle beta. So what happens together? Together clearly happens rotation about the same axis of alpha plus beta. Yes. So if we have rotation matrix R, which produces this rotation, then it has the property that first alpha then beta produces the same rotation like directly alpha plus beta. Yes. So it is clear that at least we have one example, but there are actually more. For each Lie group, there are infinite number of these subgroups with this property. I just wanted to show that it can be very simple. And now the question is that how we compute these subgroups, we will show in a moment. But first I will present some consequence of that for example, iteration of this property. That this property has some consequences that if you iterate it, you obtain something very interesting. So start with 3 parameters, T1, T2, T3. So if you call this T and this S, then you obtain T1 and A, S, which is T2 plus T3, but again this is T2 multiplied by A T3. So altogether it is A T1, A T2, and A T3. And hopefully it is clear that if I put plus T4, it will be the same T5 and so on. So in general, if I divide this T, well, we want to find T, yes? Sorry, yes. So I divide this T as T over N plus T over N times. So I obtain that AT equals A T over N multiplied by T over N times. Now, if N is a big number, so t over n, which we call epsilon, goes to 0 for fixed t. Yes, t is some fixed parameter here. But a epsilon is a0 plus epsilon a dot 0 and so on, which is 1 because of this property, plus epsilon some constant metric c, and this will be negligible because this is the form how any curve starting from 0 looks like. You remember that we studied this matrices C, and we introduced actually Lie algebra in this way for any curve. Now we have, once again, this G. Here is the unit element, and we studied some AT, and this was matrix C, symbolically, of course. So what is interesting that if you know this, actually if you know this C and nothing more, because everything else is unit and epsilon, you can compute AT by multiplying a big number of A's of this form. Yes? So in a sense, AT is AT over n, which is this matrix, 1 plus T over n, which is epsilon C, to power n for n going to infinity. So what does it mean here? That if you want to make a rotation by angle alpha, you can divide this alpha in 1,000 small pieces and then do repeating 1,000 of small rotation of the angle alpha over 1,000. And you obtain the same. Or 1 million or bigger number, yes? And actually what is interesting on that all information is actually in this matrix, in the limit, yes? Because before limit you have some higher derivatives at 0, but in the limit only the first derivative makes sense. So maybe you remember that by this limit, for numbers, we obtain some interesting function, namely exponential for functions, but it's not completely clear whether it holds for matrices and what does it mean, the exponential of matrices. But we will have a look in another way and come to this exponential, that we again start with the definition equation and compute one derivative, namely derivative of this equation with respect to s at 0. So what does it mean in plain English? It is a t plus epsilon minus a t plus 0 over epsilon. The derivative, epsilon goes to 0. So what we obtain at the left-hand side with this derivative? Derivative with respect to this guy at 0. Again, a t plus, because of z, s is now our variable now, minus a t over epsilon. It is what? What is this in the limit of epsilon goes to 0? Sorry? Yes, so it is, C is at 0. This derivative at 0 is C matrix, but this is actually what by definition? Derivative, which derivative is this one? Yes, derivative of A with respect to t. Yes, so by this operation, here we have something like two variables, but there are no two variables that t comma s. It is t plus s. That's why the derivative with respect to s at 0 is the same thing like derivative with respect to t in general. At t, not at 0. At 0, this is c, yes, but in general it is not c. So at the left-hand side, we obtain this, and at the right-hand side, this is constant with respect to c, so it is just repeating. And here we have really a dot at 0, because this is derivative for s equals 0. And this is c, constant characterizing the very beginning of the curve. So we have an equation a dot equals ac. And I will write that at the same time it is ca, because here we can interchange this t plus s because it is just the sum at the left-hand side. Yes? This means that also at the right-hand side it should be reversible. And if we put s here and t here, we can do it because of the structure of the left-hand side. Otherwise, it will be non-compatible equation. Yes? So then we will have c from the left, the derivative. So it doesn't matter where you, in general, of course, matrices do not commute, but these two matrices do commute. So here we have a differential equation with the property that the solution starts at unit matrix, and we have to solve it. Now, this is a matrix equation. So it is this matrix d over dt equals the same matrix times c, which is constant. And this matrix is AT, and here is AT. This matrix equation of this structure. So what is the type of the equation? Here are matrix elements. So for example, element 1, 2 dot comes from some matrix multiplication. So there are some linear combinations of other matrix elements here on the right-hand side. Yes, because these are constants, and here are the same variables like here. So for example, for 1, 1, you have to multiply this, and so on. But this and this is just linear combination of some matrix elements, so unknowns. Yes. So it is what kind of equation? Can you make some classification? Not all equations, but this equation. It is ordinary, partial, a system, and so on. What is it? Are there partial differential equations? No, ordinary. System or just one? System. Linear or not? Yes, it is system of a lot of n squared variables unknown, and this is the system of linear ordinary differential equation with at time 0 you should have something, zeros or ones, yes, for these variables. So in principle you know that it is not a problem to solve such equations, and maybe you know from some course of linear differential equations that they can be expressed in terms of some exponential in general. So it holds also here that I will directly write the solution and we will check that it is true. Yes? The solution is e to tc which means, by definition, the matrix which you obtain by Taylor expanding the function e to x. Yes? So it will be 1 plus tc squared over 2, so t squared over 2 factorial c plus to infinity. So here is just one expression, but they are components of this matrix. Yes, there are n square solutions of this system. Well, we can check that if you put dot here, you can make derivative with respect to t of this series. By the way, the series converges. You can prove that. You know that for n equal 1, it is just 1 by 1 matrix. It is usual exponential. For bigger n's, it is already maybe not usual exponential for you, but you can check that at each point in the matrix, you have a series which is convergent, so it gives some solution for finite matrix C. Any finite matrix C, it is some concrete function in each place of this matrix. So, if we do the differentiation of this T here, we get what? Here it is C plus T C squared plus so on. And if you put C either in the left-hand side or right-hand side, for example, I put it to the right-hand side. So what is here? For obtaining this C, you should put here 1. Then if here is C, here is plus TC and so on. But you can, in the same way, put the C to the left-hand side and obtain the same series inside. Yes? And this is A, again. So, an important fact is that the solution of this equation plus this condition is given by this series. So if we are able to compute this series, I mean that to sum it somehow, to write explicit matrix, which is equivalent to this series, we have explicit solution of this equation, and it is called one-parameter subgroup. Why it is y-parameter subgroup? Exactly because of this property, that it is some curve, but very specific curve. When we derived the Lie algebra, in principle, we started with studying any curve starting from 1 and smooth. Yes? Now this is very, very special curve. It is of the same type, but it cannot go as we wish with the same C. Why it is possible? It is trivial fact that what is this C? It is A dot at 0. What is this? Practically, it is the starting velocity of this curve. But you can have a million of curves with the same starting velocity and different future, yes, and still smooth. Now, this is one of them, but very special one. Of course, it also has this C as the starting velocity, but somehow this C is enough information for the whole future of the curve. It is very interesting. And from this, you see that it is a subgroup that, well, write another picture, that here is 1, here is something somewhere your time t, here is somewhere your time f, s, I mean ATAS here, yes. And here is t plus s, still at the same curve. That's why it is one parameter. This guy is the parameter. That's why it is called one parameter. But subgroup means that if you multiply 2 points of this path of this curve, you obtain the result again on this curve, always, for any t and any s. So just one-dimensional subgroup inside more-dimensional Lie group. And we see from the explicit formula that it is uniquely given by this initial velocity, so to speak. Yes, this element of Lie algebra. So we have a bijection. Lie algebra versus one parameter subgroups. For any element of Lie algebra, you have exactly one parameter subgroup and vice versa. We computed a general one parameter subgroup and we found that it is in correspondence with element of Lie algebra C, always. So there are analogs of these rotation matrices in a plane, which have also this property. So how here it looks like? It is some RT, which will be rotation matrix with respect to some KT. We will see it. Well, AT is rotation matrix about the angle KT. So it is uniform rotation. Uniform rotation in the plane is exactly one parameter subgroup for the rotation group. But we will do computations for several groups and we will see even in three-dimensional rotation group how it looks like, and this will be clear. So for some particular groups, it is possible to compute these subgroups in the sense that to sum this series and obtain a closed expression. And it can be done sometimes quite easily. So I will do here these computations when it is very easy, and when it is a little bit more complicated, but it is still very useful, will be left for the exercise, maybe for Wednesday, if you are sufficiently quick, or the next week. So I will start just to have some feeling that how it is usually done with SO2 group. So we know already this formula, and we want to find the most general C for SO2. So we remember that if G is SO2, that Lie algebra is small SO2. This is just how it is labeled. But now what is it? They are 2 by 2 skew symmetric matrices. Yes, it is X transposed equal minus X, always for SON. So we have now 2 by 2 matrices, which are skew symmetric. That means we have zeros on the diagonal because of the skew symmetry, and sometimes something here and minus this something here. So we can write that it is A times 0, 1, minus 1, 0. That means it is just one-dimensional linear space. This can be taken as a basis. And if this is capital X, general element of this Lie algebra, then this A is x1. Yes, in general, x can be decomposed in this way. So we see it explicitly, very simple example. And in order to make computation, we will call this matrix epsilon. It is useful to understand that this is just Levi-Civita symbol written as a matrix. Levi-Civita symbol has, in general, many indices, but in 2 dimensions, it has just 2 indices. And if something has 2 indices, it can be written as a matrix. So this is just epsilon ij, when I and j go from 1 to 2. So it is possible to draw it as a 2 by 2 matrix, which looks exactly like this. Here is, this 1 is epsilon 1, 1, 2. Yes? And very important thing is that what is the result of multiplication of 2 such matrices? So what is E squared? Why it is important? Because you see that here we have powers of C's. So we, in principle, always to compute the series, the sum, the series, we have to compute all powers and somehow to sum it. But here it is very, very easy because of this result. That how much is it, the power, the second power of this matrix? Can you see it? So here it is minus 1, here it is 0, 0, minus 1. Yes, all together. So it is minus unit matrix. And that's why the complete computation is very simple, because of this fact. So what is the series? The series is E to TC, and now C is number A times epsilon. So it is T of A epsilon. T and A are numbers, and epsilon is a matrix. Yes. So what is it? It is unit matrix plus first order, yes, TA epsilon plus 1 over 2 factorial, the square, that means T square, A square, epsilon, epsilon, plus 1 over 3 factorial, T third power, A third power, epsilon, 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 and so on to infinity. Now, this is minus 1. So, what is this then? And what is the 4th power? What is this then? Minus epsilon, and here is minus 1, minus 1, it is plus 1. Yes. So, what we see that it is an infinite series whose each term is either multiplied by matrix, unit matrix, or the matrix epsilon. Here is unit matrix epsilon. Here is once again unit matrix, once again epsilon. Once again unit, once again epsilon. So we can write it as unit matrix times something plus epsilon times something. Yes, just to collect all the terms. Now, what is here? Unit matrix here is with number 1, here is with number minus TA squared over 2 factorial. Here will be, as you can check, plus something and so on. And what is the constant with matrix epsilon? It is where? It is here. TA From here is minus 1 over 3 factorial t third, a third, and plus something, the fifth power, and so on. So they are very well-known series inside. So have a look that we somehow changed the summation of matrices to summation of just simple series, which we moreover know what they are. Here is cosine of TA, and this is just sine of TA. So we have already nice result that AT equals A to T. Well, I used here X, and before I used C, so say X is. Now, what is cosine of TA multiplied by unit matrix? It is cosine TA, cosine TA, and 0, 0. Yes, 0, 0. But from here we have something which is only here and here, and it is sine TA here and minus sine TA. So this is the closed, nice, simple result. And what we obtained, that for SO2, the matrix is parametrized by just this number, because it is one-dimensional Lie algebra. There is only one except for the t. T is here, but this x is parameterized by a, yes? And what is this? If we use this 2 by 2 matrix for multiplying columns or in xy plane, it is just rotation with this angle. By the way, I think that in opposite direction. Check. It seems to me that in this direction. It is not important, but just not to have a mistake there. So you see that we, first of all, were able to sum the series of these matrices. We obtained a simple result, and we even know what is the interpretation. That SO2 is the group of matrices which perform these rotations. So we obtained such matrix, which is okay because this will be one parameter subgroup of SO2. So each matrix should be a matrix from SO2, rotation matrix in two-dimensional plane. Okay, we come, and even what is interesting that we obtained arbitrary matrix in SO2. Yes? Give me any matrix in SO2 and I will give you T and A in order, such that it will be your matrix. Yes? There is also an important mapping, which in general, which is called exponential mapping. It is always given this matrix, and it is given by C or X. C goes to E to C. So it is one parameter subgroup with parameter T equal 1. So if you have C here, you construct AT equal now E to TC, and if here is T equal 1, this is the result of the mapping. So this mapping maps this vector, this C, to an element of the group, which is E to 1 times C, by definition. Or exp C. So for example, here, it is the result for t equal 1. So here put 1 and you obtain cosine A, sine A, and so on, as the result of exponential mapping that this matrix, which is a general matrix, yes, it is X, general X in our Lie algebra, goes to cosine A, sine A, minus sine A and cosine A. This is exponential mapping for SO2. And if you have mappings, as usual, they can be surjective and injective and so on. You can study this. And this mapping, the interesting question, is this mapping surjective? Surjective means that it covers the whole image. So for any group element of SO2, is there some A that by this exponential mapping you obtain your favorite group element? Are there different group elements than those? No. So this is surjective mapping, yes? Here. Such Lie groups are called exponential Lie groups with this property. So exponential Lie group have this property that if you compute their exponential map, it is surjective. What does it mean in practical terms? That if you compute e to x for arbitrary x, you obtain all elements of the Lie groups. That there are no elements in these Lie groups which cannot be written like that. This is not the general property of all Lie groups. That's why this concept is introduced, that in general it doesn't hold. There are elements which cannot be written like e to x, but if it is true, your group is more interesting somehow that each element can be written as e to x for some x from Lie algebra. Sometimes there are trivial reasons why this doesn't happen, this surjectivity. For example, what if we computed O2? Yes, what about the case O2? That means small o2. This O2, I think that we had it at the exercise. Is that how O2 looks like? That SO2 is given as a circle in some, well, all matrices 2 by 2 can be interpreted like some R4, 1, 2, 3, 4, yes? For any matrix 2 by 2. Now, this kind of matrix gives you some curve inside, say parameterized by this A, yes? And because cosine and sine are cyclic, they are repeating after 2 pi, it is some closed curve, one-dimensional closed curve, which is inside this R4. So there is some S1 inside this R4. It's given by this formula, that A goes to this matrix. Now, if we have not SO2 but O2, there is more complicated parametrization. Was it the case for the exercise that we discussed this, or there was something like that? I think that exactly this example. So O2 are either this or some other matrices with determinant -1. And when you think it over, they are just two one-dimensional spheres or circles. It is something like you have some set, and here is one S1, and here is another S1. This one S1 is O2 is SO2 subgroup, and the second is this part of group with determinant -1. They have no intersection. The determinant is either 1 or -1, so you cannot have a matrix which is on the intersection. So it looks something like that. And now here is the Lie algebra. What is the Lie algebra, this one, in comparison with this one? In general, this S means that unit determinant. Yes? If you think or remember, Lie algebra of SL group is given by matrices with trace equals 0. 0 trace matrices. Yes, so now this Lie algebra were matrices like that. If you add condition that in addition to this I want 0 trace, what we get? The set of these matrices with additional property that only with trace equals 0. What do we get? The same thing, because the trace is already 0. Exactly. Yes, the same thing. So what does it mean? That this Lie algebra is the same Lie algebra like for SO2, and this is the case for SON and ON always. So we have one-dimensional Lie algebra now, something like that. That's 0, and it is practically R. Because it is one-dimensional, the commutator is automatically trivial, 0. Because in one dimensions you have no possibility, think it over, of this anti-symmetry. There is no room for it. So our exponential map goes like that, from one-dimensional linear space to this one-dimensional manifold. But our manifold has two pieces. And it holds that this exponential map is continuous map. You can think over this. If a continuous map maps something like real line to something which have two pieces, you have just choose to which one you go, but not to both. Yes? Think it over. That continuous map of this type of manifold R to this type of manifold given by just do two pieces of S1 can only go to one of them. So for example, we know that what we know that 0 element goes to unit matrix, yes, and unit matrix is in SO2, say here. Unit matrix is on the subgroup SO2, not on the second part of this O2. So because one element goes here, we know it, all other elements also should be here. So no element, this is not possible to go into this other part of the group. Because of continuity and the fact that one element goes to the right part. So here, in this case of O2, it is not surjective, this mapping. But the reason is clear. There are two pieces, so it cannot be surjective. If we believe that it is continuous and so on. But what is more interesting that there are Lie groups which have just one piece. There is no situation like that. Quite simple. And an elementary example is group, I think, SL2R with Lie algebra SL2R, which has just this group. It is not completely easily visible, but you can compute that this group has just one part. It has no more parts. And exponential mapping doesn't cover the whole group. In spite of that, you have one part. You compute exponential mapping. It is one example. I don't know by heart the number of the example. Yes, but I can tell you because yes, it is 11.7.14. Yes. So have a look to 11.7.14 in the book. Of course, the best strategy is to do it yourself, this exercise, or maybe do it for us here on these recitations. Then something like here is computed that summation of the series is done somehow. Yes, because it is not very complicated. And it is not at the first sight visible, but if you have something in hint, you can check something check that here the fact like that happens. Yes? And the fact shows you that it is not surjective, this mapping. It is still maybe that, well, it is not completely trivial to show that it has just one piece, this group. Yes? But if you believe those two tell you that there is just one piece, then this is an example that exponential mapping may be not non-surjective in spite of the fact that there is just one piece of the group. So it is not always trivial like that. If you have two pieces of the group, it is okay. Something like that can happen. I see it. Yes, but if it has just one piece, it is something strange that one piece of group and exponential only covers a part of this, and you cannot go to some other part, which is altogether it is just one part. Yes. Now I will do one more computation, which usually I put to exercise, but there are some brothers exercises. One is 11.7.13 and one is 11.7.12, I think. One of them is is SU2, and another one is SO3. They are a little bit long exercises for one page, each one page this and one page this. There are points 1, 2, 3, 4, 5, 6, 7, 6, I think, in both of them. And this is a little bit more complicated. So everything you should do in all detail. Yes, they are very important for any physicist, at least, because these groups are of extraordinary importance in physics. Rotation of our space, and SU2 is also very interesting for some reasons. So it is a good idea to know about these groups as much as possible. And one part of this useful information is connected with this one parameter group and so on. So I will do here now this SU2. It is a little bit similar to SO2, but a little bit more complicated, not too much. And I leave SO3 for recitations if somebody will be interested. Yes, it is. You can be inspired by solution of this here, but here you will see something happens here, and here it happens in third order, which here happens already in second order. So this is the more complicated situation, that you should compute 3 terms in SO3 and just 2 terms in SU2. But fortunately, just 3 and no more terms are needed to compute here. Now, so I will start from the very beginning. SU2, they are matrices with this property and this property because of S. And small SU2 is what? From here you have anti-Hermitian matrices. So we want first to write the most general anti-Hermitian matrix, 2 by 2. Yes? In order to find the most general element in SU2, then from the most general element we find the basis of this linear space, and then write this element in terms of this basis and write down the exponential and try to sum it. This is our strategy. So first, anti-Hermitian matrices. The first step, write the most general 2 by 2 complex matrix. C plus ID and alpha plus I beta, and I don't know what, X plus Y. So this is the starting point, the most general 2 by 2 complex matrix. You see that it is 8-dimensional real linear space. Yes, 8 real numbers needed. But now we have X plus equals to minus X and trace of X equal to 0. So this is because of being anti-Hermitian, and this is because of this S. So traceless matrices. So for example, from trace X equals 0, we see that here should be minus A and here should be minus B. Yes, these two guys should cancel. Then write down explicitly what does it mean to be anti-Hermitian. You will have another conditions for these remaining numbers, and you will see that you will finish just by 3 number set. See 3 real numbers inside, from 8 at the very beginning. And you will see that you can write it as K1 times something plus K2 times something else, and K3 plus something still else. 2 by 2 anti-Hermitian matrices with trace equals 0. Yes. Now it is very good for computation to use Pauli matrices. Pauli invented them in 20s of 20th century, so some more than 100, about 100 years ago. And they look like that. Did you meet these matrices somewhere in some physics course already or not? So you will meet it in quantum mechanics, probably in summer semester when you will study spin in quantum mechanics, spin 1/2. For description of spin, it was invented by Pauli, and it is still used. It is perfect for manipulations with computing of spins, including quantum computing computations, because they are working with spins 1/2. So, what about these matrices? Are they anti-Hermitian or not? If you have a look. For example, this sigma 3 is what? Hermitian, anti-Hermitian, or what? Or other? What is Hermitian? That if you make Hermitian conjugation, you obtain the same. Hermitian conjugation is what? Transposition and complex conjugation. This is real. So complex conjugation is trivial. It is symmetric. So Hermitian conjugation is doing nothing. Yes. So this is Hermitian matrix. Yes. If you check, this is more complicated, but check that it is also Hermitian matrix, and this is also Hermitian matrix. So all of them are Hermitian. Notice that all of them are traceless. Yes. Here it is trivial, and here it is trivial, and here it is a bit non-trivial, that you should sum 1 minus 1 and compute that it is 0. Yes? But 2 zeros are a little bit simpler. So they are Hermitian and traceless. But what we need are anti-Hermitian and traceless. Did you remember from linear algebra, if you have a Hermitian matrix, how you produce an anti-Hermitian matrix, or vice versa? Very simply. By multiplication with I. Yes? If your matrix has the property that y plus equals y, then if you take x equal y, I, y, then your x will be anti-Hermitian, and vice versa. So there is a bijection between Hermitian and anti-Hermitian matrices given by multiplication by I. And if you have those Pauli matrices, which are Hermitian, just multiply them by I, and you will obtain some basis of skew Hermitian matrices, anti-Hermitian matrices. This I is very important. Without this, they should be Hermitian. Now, this is a basis in our space, so we can compute these commutators, JK, and compute structure constants. And of course, if you take any non-zero multiples of these basis vectors, you also obtain basis, another basis of this Lie algebra. So this is a basis of our Lie algebra. Yes, I forgot to tell that we have some basis. If you compute commutators, you will see that here you obtain, do the computation, epsilon L JKL with some lambda. You can compute what is the lambda. It can be simplified by multiplication of some number in order to get rid of this lambda. If you will take some K1, E1, and K2, E2, and compute commutator, you will have K1, K2, they jump up, and they can cancel the bed constant here. Yes? So play a little bit with these commutators and find that if you take a basis which is minus 1/2 of this basis, so it is of course still the basis because it's just minus 1/2 of the old basis, but it has nicer commutation relation. There is no lambda here, just 1. Yes? So this basis has nice property that Ij commutation relations is epsilon Ijk Ek. So once again, this I is extremely important. Without this I, it is not anti-Hermitian. This 1/2 is not so important, but it is nice to have, nicer. for some future computations. Now, how the general element of the algebra looks like? It is a real linear combination of these bases. Yes. So, general X is some K I E I. So this is some triplet of real numbers, the components of this X with respect to this basis. And we can write it as alpha Ni. General vector can be written, it is like vector in R3. It can be written as a unit vector and the length of the vector, yes? So this is the length of this K, and this is a unit vector part of this K. What does it mean? Put all together that it is minus 1/2 I alpha N J sigma J. So it is parameterized, the general element is parameterized by one unit vector and one constant alpha. And this is usually written as n dot sigma. N dot sigma is something like scalar product, but it is just scalar product for the purpose of writing some expressions in this sense. Yes? Otherwise, what is it? It is 2 by 2 matrix. It is it is skew Hermitian traceless 2 by 2 matrix, because the basis is any linear combination should be. How it looks like? Here are the matrices. So n1 sigma 1 is n1 times this. It is n1 where? Here and here. Plus n2 sigma 2 is minus I n2 plus I n2 and plus n3 sigma 3 here n3 and here minus n3. It is just this matrix for any unit vector n. Now we can easily compute, because it will be useful, that what is this matrix squared? It is this matrix squared. So put two such matrices, make the computation, and you will see, yes, squared, you will discover it is 1/2 n1 squared plus n2 squared plus n3 squared, 0, 0, and here is the same guy here. And what is this matrix? Here is, once again, n1 squared plus n2 squared plus n3 squared. It is what? Number 1, because it is unit vector, yes? Here is also number 1. So it is altogether unit matrix. And this is the essence of that we already won to sum up this series because of this property. We had something similar in SO2. So what is AT? It is E to T S X, yes? Or E to minus 1/2 alpha n dot sigma I. So I here. This is our one parameter group for X is what? Is minus 1 T, so also T here, sorry. Yes. Everything without T, which is there, is X. Minus alpha n dot sigma. So let's do the series. It is unit matrix minus this x, or plus tx, yes, plus tx, plus t squared 2x squared plus just another term, third power, x to the third power, and so on. Now, this x is here. But what is x squared? There is minus. Is I. Yes. Also here. So what is x squared? It is this number squared times this matrix squared. But this matrix squared is unit matrix. And this number squared is easily computed. It is minus alpha squared over 4. Yes, it is minus alpha squared. Okay, it is something not very nice. Is it true? Minus is because of this I. So, and unit matrix. Yes, yes. Maybe it is okay. Here is what? Here is first this guy, third power, but the second power is just 1, so the third power is this guy, or minus 1. It is what? 1 or minus 1? I don't want to recompute it.
Should be the same because
no, it is plus 1. Yes. No. This is really, I think it is plus 1. Yes. Because, for example, we can check it for any concrete unit vector. For example, 0, 0, 1. For 0, 0, 1, we have just sigma 3 squared. And if you check sigma 3 squared is plus 1. Yes? Okay, so it is plus. So here it is again n dot sigma because squared is already 1. So it is times everything this put without t and yes, without t. Yes. So something to third power. Yes. The point is that the fourth term is again proportional to 1. The fifth term is proportional to n dot sigma, and so on. So we can again do the same trick. Unit matrix times something plus, maybe the best thing is I n sigma times something. And if you have a look on this something, it is quite easy. You will see that they are cosine t alpha over 2 and sine of t alpha over 2. This 2 is very important. This fraction, 1/2 alpha, not just alpha. It is the difference with respect to SO3. There will be somewhere alpha, and here it will be alpha half, which makes big difference in the application of this. So what we have, we once again have in closed form our one parameter group. Yes, it is unit matrix times something plus this matrix times something. If you do all details, it doesn't look very, very nicely because of this term, but using this abbreviation n dot sigma, it is very simple. Now, the question is whether it is surjective. Now, the exponential map. Exponential map, small SU2 to big SU2. You can have a look, and this is the content of the last two parts maybe in the big exercise. I will not do it. The last two parts are that check that the definition of the group, if you have an element Z, W, and I don't, Z1, W1, Z2, W2 in general, two complex numbers which satisfy this equation, you will see that our group is actually as a three-dimensional sphere in four-dimensional space. Yes. It is written there. So it is quite nice and simple manifold. By this parametrization, you can see it very easily. And then you can check, it is the last point of the exercise, that if you do exponential mapping of the whole Lie algebra, whether you get whole SU2 or not, and the result is positive again. It can be seen from the parametrization of the group. Yes? If you know the parametrization of the group, and you know this technical result, that this is the most general matrix which is in the image of exponential mapping. Because for t equal 1, put here 1, and this matrix is the most general matrix of exponent of any element of small SU2. Now the question is, if here is any element of big SU2, can it be written for some alpha and for some n? And the answer is positive. Yes, it is visible that it can be. So once again, this is exponential map. Exponential group. So this example, I will only tell what is interesting on the result. The way how to obtain is just sit down and try to learn something in this example, SU2, and do the same, something like the same for another group. So first, what is the basis? I will maybe comment this basis. Small SO3 are skew-symmetric real numbers. But 3 by 3, it is something like A, B, C, 0, minus A, minus B, C, minus C, and 0. Yes, so you need three numbers. That means it is a three-dimensional linear space. That it is linear we already know, and now we see that it is three-dimensional because general skew-symmetric 3 by 3 matrix has just three real numbers inside. So it can be written by A times something plus B times something plus C times something. You can compute these matrices, which are these three somethings. And there is a nice way how to write them, all of them, that you introduce matrices Ly, I equal 1, 2, 3. They are basis matrices, which are practically those guys, but somehow reorganized. So definition is that ith matrix, jk element, because it is a matrix, is minus epsilon ijk. Yes? So for example, L1 is what? It is, because of that, jk are matrix elements now. Yes? So there is, we see that anti-symmetric matrix. So it should have three zeros here. Now what is here? It is 1, 2 element. So here should be 1, 2. Here is 1. Here is 1 because it is L1. And here is 1, 2 element on epsilon 1, 1, 0. Yes? So because here is 1, here should be the interesting part is 2, 3. It is where? It is here. Then epsilon is 1, but it is minus, so here is minus 1. Then here should be 1 because it is antisymmetric, and all other positions are just 0. So write down all other L's, that means L2 and L3, and you will see that really this is a basis of 3 by 3 antisymmetric matrices. Practically, just do this computation and check that those 3 matrices, L2 and L3, 1, 2, 3 matrices, are exactly in these brackets. But it is not so that here is L1, L2, L3. They are some reorganized, with some minus also and so on. But this way of defining the base is very useful because of this formula. You can now compute with this basis a lot. So, what is the most general matrix from this Lie algebra? It is KI, LI. Yes. Again, here L alpha and Ni. So the most general X is alpha N dot L. It is abbreviation of N1, L1, N2, L2, and so on. Nothing more. It is symbolically written as a scalar product. If you compute now e to tx, that means e to t alpha n dot L, what you should do to compute the one at the beginning, then linear part, then quadratic part, third power, and so on. So the question is how this guy behaves when you do the second multiplication and third and so on. And it is not that easy, that already second is unit, but if you compute the first order, second order, third order, the fourth order is just repeating of these first 3 guys. Yes? So the whole matrix is unit matrix times something, something else times something, plus something else times something. They are just 3 basis terms and just numerical sums inside. It is more complicated than SU2, a little bit, but useful computation. If you do that, and then you write down your matrix, it will be a rather complicated matrix, but you want to know what it does. So you apply, because it is 3 by 3 rotational matrix, we know. So let's apply it on R, and we will obtain rotated R. And we are interested how much rotated, which angle, which axis. Yes? And because of the structure of the matrix, we are able to do it. And we can see that this is the angle of the rotation and this is the axis of the rotation. This is the way, this is the reason why this is perfect parameterization for our purposes. Yes? That this matrix is rotation around axis given by n. If you have R here and n here, then this is an axis, and here you can make a rotation around this axis. Here will be AR somewhere rotated, and if you have a look from this n, here will be T alpha angle. Yes. How we can prove it? That first of all, you will have to derive the matrix that how it looks, this rotation around n. And it can be done by elementary means, that you have some vector n and vector r, and you want that I don't change the length of the vector, I am going around. By some scalar and vector multiplication, you can compute what happens with r after rotation with angle alpha around this. This is elementary problem. If you know what you want, if you know to compute scalar product of vectors and the vector product of two vectors, and you know what does it mean, then you can do it. And you obtain these metrics, yes, without big signs like that. And now you compare small science from the picture to big science of computing of some series, and you will check that, oh, these are the same matrices. So from that, we know that this matrix is just rotation matrix for angle T alpha around this vector n. So this parametrization is very practical because the parameters has direct meaning that we have here it is rotation around this by this angle, T alpha, yes? And it has even more, you notice that we have those alpha and n also for SU2 and also for SO3. We will have at the end of the semester something which is called covering of SU2 over SO3, and for this, these formulas are also extremely useful. This covering is which is very famous and quite useful to know. After this semester, you will see it. It can be computed in not so complicated way if you have parametrization of both groups in this way, prepared for this big computation of this two-sheeted covering, which is, how is it called? So that's why I think that all these computations are very useful for any physicist and also mathematicians who wants to know something about these groups, that these SU2 and SO3 cases deserve your work and some maybe 1 hour, one exercise and 1 hour. The second exercise is not wasting of time. It is usefully spent time, in my opinion. Okay, I can start another important point, and it is called derived homomorphism. It uses this concept of one parameter subgroup. So imagine we have two Lie groups. Here will be G and H, and we will have a homomorphic mapping of the left group to the right group. Here is unit element of G. Here is somewhere unit element of this H. And we imagine that both matrices, both are matrix Lie groups, nothing more. So recall that homomorphism means that it preserves the product and all structure, inverse and unit element. And including unit element, that G element, unit element goes to unit element of H, and also inverse. Now, imagine that here we have one parameter group, which we know that has this structure. Yes, that here is X, the initial velocity, and it is given by ETX. One comment may be useful. A side note, sorry. I could tell it sooner, but I forgot. This is a very strange curve that the whole curve is known whenever as soon as you know this initial velocity. Yes, in general, in mechanics, do you know some example that some type of motion that when you know initial velocity, you know the whole motion? Do you know some motion of this with this property? It is a free motion in Newtonian mechanics. If you start with some velocity, the whole life you have the same velocity. So if you give me your initial velocity, and if you give me the information that it is a free motion in Newtonian mechanics, I can draw the whole picture, yes? Notice that something like this happens here. If you give me the initial velocity, it doesn't look very much like Newtonian mechanics and so on, but this property is very similar. The property that if you have initial velocity and you go then straight and uniformly, is a property of some curve in differential geometry, which we will study in detail in chapter 15, that means the next year, and it is called geodesics. It is the generalization of the concept of the straight line. Now, maybe you know the geodesics as the shortest line. They are two completely, well, not different, but differently formulated problems. That first is construct a straight line in the Riemannian manifold, and the second one construct the shortest line in the Riemannian manifold. It turns out the shortest line is the straight line. Parametrization is not important for shortest line. For the straight line, it is important, but because in Newtonian mechanics we are going uniformly along line. Yes, there are two properties. So geodesics in full is this straight line when we go uniformly along this straight line. And here it turns out, or if you want to formulate this geodesics, you know you need another connection, another structure on your manifold. For studying geodesics, you need this structure. Yes, it is called linear connection. It is not the metric tensor. If you have a metric tensor, for example, if you need to compute the shortest path, you need metric tensor. Yes? This connection can be not computed from metric tensor, and in spite of that, you can construct geodesics. Yes, it is true that in general relativity, if you studied something, this connection is given by the metric tensor, but in general it is not so. So what is really important for geodesics is this linear connection. And it turns out that these one parameter subgroups are actually geodesics on Lie groups when some particular connection is defined there. Yes? So it looks like geodesic by the property because it is geodesic actually. But for us now it is not important, but I just want to turn your attention to this strange property that it is a curve given in full by the initial velocity. It is not typical for curves, but it is typical for geodesics. And here it really happens because it is a geodesic. Yes, but it is somewhere in the 15th chapter, at the very end of the 15th chapter, this exercise that show that it is geodesic of this and this connection. Oh, so I will not finish this story because it is just 30, yes, or even 31 because I made a mistake on my clock. So you get by free 1 minute in this lecture. So at Wednesday there's a recitation and we will go out on Thursday with this idea, yes?